a really interesting multi-year project that has been a huge personal investment for them, I know, about porting SBCL to a challenging, unique hardware platform, the Nintendo Switch.
Thank you. You don't need to know. Stop it. Okay. So for those not in the know, the Nintendo Switch is this kind of device. It's a game console. And so as a game console, historically these things are very locked down. They have their own hardware and stuff. This has been getting a bit better recently. So they use more and more off-the-shelf stuff with some weird twists. So we have an ARM 4 64-bit processor. Excellent. ARM is standardized. It's no weird extra instruction stuff. Great. The OS is called Horizon OS, or NX OS, as it was in the beta stage, which is a proprietary microkernel. Not so great for us. And then the SDK, all the game stuff, it's all C++ and all only for Windows. So, great. So you can imagine the initial challenges that we're facing as just considering this project, So everything is proprietary and under NDA. If you Google for stuff, you find all the illegal things, or the gray legal things, which is like people are reverse engineering the hardware and the OS and like jailbreaking and stuff. Everything else is unpublished. So the OS is not BSD or even POSIX fully, which is, so we need new abstractions for that stuff. And then, now that we have access to the SDK and all this stuff, we can look a bit deeper into things, and we realize there's no inter-thread signals. And if you know a bit about GC, that's going to make you wince a bit. Even worse, we're not allowed to create executable pages. If you know anything about Lisp, this is going to really make you scared, because this is how we do pretty much everything. And then if you know details about SBCL and so on, we have ASLR, which is like when the program boots up, it puts memory in random locations, so it's a security feature. And SBCL does not like this, because historically it does other things.
Okay.
So, yeah, go ahead.
Oh, so we have all these problems, and how do we solve these problems? Okay, so we have to only publicize our own interfaces. That's okay. And then how do we deal with C++? Well, SBCL is written in C, but C and C++, they can work together. You have to munge the build systems a bit, but this is actually a manageable problem. Maybe there's some C++ keywords inside the SBCL definitions. It's okay, we can figure that out. For the GC stuff, okay, well, we have to do save points because we don't have inter-process signals. On Linux, these are used for the garbage collector to stop the world when you have a multi-threaded SBCL program. But actually on Windows, we don't have inter-thread signals either. So there's an existing save point mechanism. But this isn't enough. There are more problems, and we'll talk about that later, because it's not that easy. And then, okay, so what do we do about this you can't create code at runtime? Basically, that's what this executable pages constraint is. And Lisp is all about creating code at runtime. Even like the object system calls compile for JIT. What do we do? Yeah, well, we have to try and compile everything as much as we can ahead of time. And so, yeah, we cannot bootstrap SBCL on the switch itself. So we need to find a different solution. So what we did was we compiled everything on Linux using it as a surrogate. So sort of like, okay, yeah, we can't do it on the actual switch system itself because we have no facilities to do that. Then we use a special tool that was developed beforehand for something else, but it's called shrink wrapping. We'll get into more details about that, but this kind of helps us with the surrogate process of using a different operating system host that allows us to bootstrap the SBCL. Okay, so what do we do about this address space layout randomization? Because historically, Lisps do not like this. Well, we just had to make everything relocatable, and this also took some effort. So, yeah, let's just talk about the history of this project a bit. So, yeah, if I remember correctly, We had some preliminary discussions on IRC back in 2022, but then we actually met in person for the first time at in Porto. And we talked about it. It's like, this would be a fun idea, but it probably makes no sense. There's no way this could ever work. But I was like very optimistic, like, I can do it. You know, I've done crazy stuff before. Let's do it. So this is like ignorant optimism. So, but then we actually came up in the next conference. We started talking seriously about it again. And Yukari was very much like, okay, let's do this. Let's draft out a contract, like work what we can do. And we did this in the airport because we were both there at the same time. Very good. And then the following months we were, very motivated, got a lot of the initial work done. And then, I don't know, there was a long break. And for the next 2 years, sort of like maybe 1 month in 2024, 1 month in 2025 this year, where we kind of got, where I was debugging the GC remaining issues after all this initial work. And then we actually got some game engine examples working earlier this year. And we even got Candra running for the first time. And, well, it's not that simple. So we'll keep going. Yes.
So the usual SBCL build system is proceeding in sort of these phases where it starts gathering system information about like what do we have, what do we want, spits out a bunch of files. Then it runs a thing called makehost1, which does a bunch of like questioning the C compiler about what are like the address spaces and like page sizes and so on. And then you call maketarget1, which actually compiles the GC and runtime bits of SBCL. And then it calls that's makehost, sorry. And then makehost2 is where you start cross-compiling stuff. So you use some kind of surrogate system that can run everything, can run arbitrary Lisp code, and you use that together with this information you gathered in the previous steps to build an initial compiler in the sort of a cold core, as it's called. And then you actually run everything else on the target system. So this is where like our main issues lie, because we can't do this step on the switch itself. So in order to adapt this, it's gotten a bit more complicated. So this graphic is meant to signify that we basically have two separate SBCLs that we build. The first one is the one on the left that we actually want ultimately, and the second one on the right is the one we use as a sort of surrogate host. So we build config and make host one twice, once for the Linux surrogate and once for the actual target we want. Then we run make target and host and target2 and user stuff on this Linux host, which is an ARM64 system. It's close enough to the switch where the assembly that it generates is compatible. So we're very lucky with that we have an actual ARM chip, and SBCL already had the ARM port and everything. So we build things with feature flags that are very, very similar to what we want in the end. And so this is fairly brittle, and it requires an extra host. So we had like the build system I developed for this is like it SSHs over into another host to do that part of the build, and then it syncs files across. And then once you actually have all of SBCL compiled, including the user code that you ultimately want to run, you have to go back to this side. And now, with the runtime that we built in maketarget1 for the switch, which uses the switch SDK, we now combine that together with the shrink wrapping step. So basically bolt on the Lisp core onto the other runtime, and then run it like that on the switch, and then it does some extra packaging stuff. And the packaging stuff and the compiler is all Windows only, so we have to run it through Wine. Right. So now we're talking about the fun bits of actually getting this code stuff going.
Okay, yeah, so we had a lot of problems just with the operating system and the constraints, the unique constraints that this hardware platform kind of gave us through its microkernel architecture that was very locked down. Because with these game consoles, the reason why they make it really hard to do anything like JIT, why they do address space layout randomization is because they're very careful about not letting people run exploits. So they really don't like homebrew stuff. You know, like these game developers think that's like bad for IP, things like this. So how do we get around that? Because Lisp uses these for non-nefarious purposes. Okay, so to get started, Lisp is very Lisp implementations such as SBCL, I mean other Lisp implementations as well. It's usually an image development based system. So what this means is that you have your Lisp objects in your Lisp image, and these Lisp objects have pointers to other things. And what you do when you create an executable or an image is that you just dump everything out literally. So all the addresses, so let's say you have a lot of data, that data has a lot of absolute pointers because objects are represented as tagged pointers. So when you actually dump an image, what happens under the scenes is that everything in your memory is just dumped to disk with the numbers as they are. And then what a runtime like SBCL expects when it reloads an image is that it just maps everything into the process as if it were still the process from before, with all the literal addresses as they were in the past. So traditionally, this is no problem because SBCL can pretend it owns the entire process space, and it can allocate address spaces wherever it wants. So it just allocates the address spaces where the previous process, the previous instantiation of the image expected things to be. So this is how dumping to core and reloading images are so fast, because you just put everything down into disk and then just read it back up into the memory of the process. So yeah, we can't do this with address space layout randomization because you're not allowed to ask for fixed addresses. So you can only ask for addresses spaces. You can only give the operating system a size. So if the Nintendo Switch says, okay, I want 50 megabytes of space for my dynamic heap. And it says, okay, here you go. And the address is completely random. And so what do you have to do? You have to relocate the objects already on disk. You have to move the objects that you had on disk into the correct places in memory and fix up all the other pointers that point everywhere. So this is almost like a GC process. There was actually support for this already for the majority of stuff, so relocatable heap, if you know that. But there were some spaces that you couldn't do this yet, so we had to change the SBCL runtime to actually support relocating all spaces. Can you go back, actually? Yes, okay, yeah, now? Okay, so, right, so the solution is we just have to do this. For code objects, it's been more difficult because even code objects, your code generation sometimes has to hardwire special addresses in the code itself. So we had to change the code also to be position independent. So if you know like position independent code, position independent executables, it's the same principle. This is how languages like C, they get around things like address space layout randomization. They just make sure that you don't actually have to assume anything about where things are in the process. So we had to change that. That took some work. But the really, really hard thing is that even how code objects are fundamentally represented in SBCL present a problem because we cannot create new accessible pages at runtime. We have to make sure everything is loaded in from disk as an ELF file and everything's in a text section because you cannot create those new pages once you've started up the process. And this is a problem because code objects in SBCL not only contain instructions, they also contain data, like the constant, like pointers to constants. So I'll illustrate this with an example later. But essentially, this is hard because you can't write into executable memory either. This is also a really common thing. Even the new M1 Macs have this constraint where once you have executable pages, you cannot actually modify the memory of these executable pages because that's a security risk. You don't want self-modifying code in a super secure system. So this is bad because your code objects are on executable pages. And these constants, you need to fix them up. One, for address space layout randomization, but second, the garbage collector is we have a moving garbage collector in SBCL. So let's say SBCL moves some objects in the heap. Do you have pointers to those objects in your code object because they're like code constants or something? And then you can't actually go and fix those pointers up because your code object is not writable. So what we had to do is we had to essentially segregate code instructions from the data in the code objects into different ELF sections offline. So we had used the shrink wrap tool. So what the shrink wrap tool does is you have this image on disk, and your image on disk is then turned into an ELF file, so that the Nintendo Switch operating system executable loader can actually read things from the sections and say, okay, this is code. It's safe to execute, put this code on an executable page at load time for the operating system. So what we did was we modified the shrink wrap process, which kind of processes your dumped image, and we segregated the code and the data so that we were even allowed to modify things. So I'll show an example now, because this is a bit confusing. So let's say you have this function f, and what it does is just cons its two literal objects together. Okay, so so how does SBCL represent the code object for this function f? Well, you don't have to get, so I'll just talk about it a bit here first. So basically you obviously need the instructions for f. So like we're gonna cons to objects, so you have the code instructions for that. But we have two pieces of literal data. We have a cons object and we have another symbol object. And these are actually represented inside the code object itself. You have a pointer to the to this cons object, and you also have a pointer to this symbol object, and then the code instructions will actually cons these two code constants together. So in the code, you have a reference from the code object itself. So we can go to the next slide here, and I mean, it's a bit difficult to explain exactly what all these pieces are, but essentially you have imagine this is your Lisp image. So in a normal Lisp image, you have a lot of data. So you have two objects up there. You have a cons object and a symbol object, and then now you have a code object. So this is all in the same memory heap. And this code object, you have a code object header, so this stuff in bold, which is the stuff to describe the code object, like the header, type tag, everything like that. Then after that, you have pointers to those objects. So in the code header, you have pointers to the constants, and they point to other places in the heap where the objects are. And the GC is free to move stuff around, and then they can fix up these pointers. Just imagine you're doing a normal GC operation. This is how this stuff works. And then after this code header, in the same block of memory, and now I'm not using raw bits anymore. I'm going to describe it with these code instructions so you actually see what this looks like. These are ARM instructions. What you do when you want to load these constants, so we have to load these constants into registers, and then we call cons with these register arguments. That's what the assembly code does here. What you do here is we do a PC relative load. So the address of this load instruction is not very far away from what the constant is supposed to reference. So in the ARM instruction set, you can do a PC relative load. So yeah, you load that object into R2, and then you load the other constant object into R1. So by loading the object, I mean just the pointers to those objects in the heap. And then all the rest of this code does is basically call cons on it and then return you the value of consing these two constants. Okay, this does not work on the Nintendo Switch. You can't represent code like this because you have your executable code. Previous slide. You have your executable code, and it's all together. Like the data and the executable code is all on the same page, and you cannot write into executable code. So this will break. You can't represent it at all like this. So what we do on the next slide is we do the segregation process. So we do this all offline in the shrink wrap tool, and what this means is that what we do is we take all code objects in the image, and we look at all the constants there and say, hey, these constants, we're going to shove it all into a writable section because there's no code instructions here. So we create a separate data section in your offline ELF file, and then we have all the constant pointers, the like raw words, in this section. And then this section will point to the actual like objects laid out in memory in the heap. And then we create this separate text section for all the code objects. And what we do is so we blank out where the constants used to be in the header, and we rewrite the code. We rewrite these constant reference instructions to point to this read-writable section. And luckily enough, ARM has wide enough reach for the load instructions where we can have all the constants in a separate section, and then just have that close enough to all the code in the image, and then just rewrite the references like this. So we introduce it's not really introducing another layer of indirection. It's more like displacing all the constants out into a separate section that the garbage collector can rewrite as it wishes, that we can relocate on startup, and then rewriting all the references in the code offline to point to that section. So this is how we solved this issue of, and remember here the constraints are, we have a moving GC, we need to relocate stuff because of address space layout randomization, and at the same time, code is special. You can't write code, you can't write into code once it's already loaded, and you also can't create new code, you can't create new executable pages at runtime. So that's how we solve this problem. Okay, so that took some work, but now we have problems with the garbage collector, because again, garbage collection in SBCL as it is requires a lot of support from the operating system. So we said again, okay, even Windows doesn't have support for inter-thread signals, and we need to use save points. Okay, so great. We just used the support already available for Windows to do save points to avoid inter-thread signals, which the operating system on the switch doesn't support. But there's another problem. So even the save point mechanism that exists for Windows relies on hardware exceptions. So to give you a nice example, okay, so a save point is basically a place in code where, let's say your garbage collector decides, I want to stop the world and start collecting garbage. You need to stop all the other threads. Now, how do you let the other threads know? Well, when you have inter-process signals, you can just send a signal to say, okay, threads stop. I'm going to start garbage collection now. What happens on save points is that the garbage collector just says, okay, I want to start doing garbage collection. I'm going to set a flag at memory locations that all other threads will periodically check. So this is kind of polling. And how the checking is done on Windows is it just does a load from a memory address. And when the garbage collecting thread wants other threads to stop, it just says, okay, let's make that memory unreadable so that the other threads, when they do this load instruction, will simply fault. And then it traps into kind of the runtime machinery that allows you to proceed with garbage collection. This is a very common virtual memory trick people use in garbage collection, which is you purposely make the process segfault so that you can handle it and do something. So the problem is we don't even have the ability to handle segfaults or these kinds of OS exceptions on Nintendo Switch. So what do? Well, we have to change the save point code. Instead of doing this clever memory management trick of purposely segfaulting, we have to make every thread kind of poll explicitly. Just do this kind of conditional check. Okay, this memory location has a 1, then we go into GC. If it has a 0, then you can keep going. So it creates a bit more code bloat, but this solves the issue. If we keep going. So that kind of works. There was this other problem of the other advantage of using the hardware exceptions for that garbage collection case was that it made some concurrency things a bit easier. When you do polling, sometimes you have to make sure that things are actually synchronized. So it was actually conceptually an easy problem, but in practice you had to make sure all of this concurrency stuff was dealt with, which is never fun. Anyway. The other thing with these hardware exceptions, that SBCL not only uses hardware exceptions for garbage collection, but it also uses it for some really critical conditions. So for example, if you pass the incorrect number of arguments to a function, it'll actually throw a hardware exception instead of calling error, or things like that. Or if you have a type error, sometimes it'll also throw a hardware exception. So what we do instead is we just tell the compiler, and this is actually not that difficult, instead of trying to be clever and save code space by using hardware exceptions, just call signal or error and let the runtime handle it normally. So we avoid having to use segfaults. Okay, the other problem, which all of this gymnastics that we did for the code relocation stuff, is that the object system requires runtime compilation for JIT. So if you're familiar with any dynamic programming language that has an object, like JavaScript, for example, most of these object systems, or Java, Java hotspot compiler, what they do is that they create new code at runtime. They JIT new code at runtime to make method dispatch faster, because they see, okay, we call it on this type a bunch of times. We can create new code that's more special, and things are fast. So the object system implementation in SBCL does the same thing. It likes to call compile at runtime. The thing is, you can't call compile at runtime because you can't create new native code at runtime because we can't set new executable pages, even though the compiler works. So this is kind of where we had to really fall back to using the interpreter. So there is an interpreter in SBCL. There are 2 interpreters in SBCL, but we had to use the evaluator in SBCL to kind of evaluate some of these method dispatch things that otherwise would have just been run through the native code compiler. So that was one part where we did have to kind of cheat a bit, where we couldn't compile everything ahead of time. And this was kind of a silly bug we found at the end, or this was all going smoothly, and then we actually tried to shrink wrap Candria, and we found that Candria, that was the biggest thing, that the shrink wrap tool itself is not GC safe. So the shrink wrap tool crashes randomly. And it crashes randomly on ARM systems, because the person who wrote this shrink wrap tool actually only used it on x86 machines. And it's more conservative, and so it's safer on x86. But we're running everything on ARM, which is very precise, so we know exactly what's a Lisp object or not. But the thing is, the shrink wrap tool is written so that this was not safe on an ARM system. So when we had a 200 megabyte image we wanted to run this tool on, it would crash. So we had to create a third SBCL host that had the memory spaces it used to be mapped away from the memory spaces that we actually were shrink wrapping on, so that the memory spaces would not collide, so that the actual shrink wrapping tool that we had wouldn't crash. So then this was something at the very, we just added another SBCL to the build project, because why not? It's too simple otherwise. Let's go to the next. And then so now we have a live demo to show you what actually works now that we've done all these backflips. And now it's going to be a surprise to see whether anything works at all.
By showing you this, I am committing a crime, but we'll just get into it. So it takes quite a while. It's still very much unoptimized, especially the startup time. But at some point, there will be image. It's loading. The switch is a potato system, so it's like the chip that it has is from over 10 years ago, and even back when it was released, it was not very good. But yeah, here it is. And if you bear with some more loading, you'll actually see the game running too. That takes even longer, so just...
I'm supposed to fill in the space now, somehow. Yeah, so... so we have this, we have graphics showing up, which is cool. I think the Switch uses, correct me if I'm wrong, but the Switch actually does support OpenGL. So for your game, so for anyone who doesn't know, Candria is a game that already is released on Steam and runs on PC, but it uses OpenGL. And so that's actually, you could just do the graphics straight away, right?
Yeah, so I didn't need to do anything special for the graphics, because like other systems like PlayStation from Sony or Xbox from Microsoft use their own graphics toolkits. So I would have had to like port the entire engine capabilities as well. But anyway, the game is running.
And then maybe you can do some gameplay. I'll hold this stuff for you.
I can't really do gameplay, but anyway, so it still hitches a lot. It still hitches a lot, as you can probably tell, which means there's still some performance stuff to deal with, but ostensibly everything is running. We can now run arbitrary code and port it over to the Switch. And like the trial examples, like there's a huge collection of example demos we also have over here. We also have like a self-testing thing. So all of these things are mostly working. Let's do that. This should be faster to load into, I hope.
Yeah. So actually, when we first got this when we first got Candria running, there was, I think it was running at like less than 1 frame per second or something, and we made some optimization to speed it up, and now you can actually. Okay, so now we have the examples.
Yeah, but I think I need to use the touchscreen input for this.
So do you want me to hold something for you?
Wait, it's actually not. They're working, okay? Trust me. This is the demo effect. Yeah, just don't worry.
Okay, sure. Anyway, yeah. Then when you run these demos, they happen as they do on PC. So we ran this for maybe a week before we decided to stabilize some stuff, because it was still crashing occasionally. And then we used that to stabilize some things before we decided to run Candria. And actually, what's really surprising is that once we started running Candria, we stopped observing crashes. Like we haven't had any crashes in the times we've tested Candria. So, I mean, the moment I say that the GC seems like it's actually stable, maybe we're gonna find a bug. But so far we haven't encountered anything crazy. And then, yeah.
So what's left to do? Obviously, startup time is a bit long. Build times are insufferably long. So remember, we need one sort of system to coordinate everything. Then we need an ARM system to run most of the build, and then we need a Windows system to run their like toolchain and whatever. Most of the things you can do with Wine, but still, you need to sync across like whatever many megabytes of your code and data over so you can do the actual build on the ARM system and then sync it back in. And yeah, it's like right now I wrote a custom build system that can like cache everything and manage that. It still takes 15 minutes. So if you want to like try out a change, you have to wait 15 minutes until you actually get to test it. So that made everything very painful. One thing we also didn't talk about here, but is like mentioned in the paper, is the debugging experience is horrid. Like, because there's no REPL, there's no runtime, no anything. The only thing you have available is this Oasis debugger, which is like in Visual Studio integrated, and it hardly works because it doesn't understand Lisp frames or Lisp data or anything. So what you get is just assembly output, and then you get to stare at that for hours and hope you get smart. Right, but the good news for optimizing stuff is that we can do this all on PC. On x86, we can use the statistical profiler from SBCL to figure out where hotspots are and do that optimization work. And we want to port in the Nintendo Switch 2, which was like released or like announced earlier and is releasing in a bit, like a couple months down the line. And that is just a question of when Nintendo will give us plebeians access to the dev kit. I have no idea about that. They're being very stingy, so yeah. And that's about it. So far, all this work, I paid Charles to do this, okay? I paid him. I didn't pay myself, but I paid him. It's a lot of money. If you want to support efforts like this and game development in Lisp, please support my Patreon. And so we can do more cool stuff. That's it.
Thank you. Thank you, Yukari and Charles. We have a few questions from online already, but I will start with one from the room.
Hi, you mentioned using SSH to compile to the ARM64 machine, I suppose. Couldn't you use like QEMU or some local emulator? Was it too slow or not working because of signals?
QEMU is so insufferably slow, you have no idea. It would take probably a day to finish a build. So, yeah.
I did actually, so I have like one of these new Apple Macs, and they have an ARM chip. So what I did was when I was doing some of the stuff, I just virtualized it on, I virtualized Linux on my machine because we were using a Linux host, but that actually was much faster.
Yeah, and I used my phone, so I had like, anyway, there's another story about like Android SBCL having its own quirks. And
So online, Max Rotten-Kolber asks, I'm wondering if ECL would work somewhat out of the box in an environment like this.
okay, so I should mention other implementations. Some weeks ago, I got CCL and ECL actually running trial, so all the compatibility stuff is there. The thing is, even on x86 on a fast machine, ECL takes hours to compile the code, and it runs insufferably slow even on the most basic of demos. I already assumed that was going to be the case, so I didn't even want to consider it, because it's just making that fast is...
And I'll just say something about other Lisp implementations. So other Lisp implementations like CCL, you know, all these image-based Lisps have the same problems that we had with SBCL, and especially with this runtime stuff. So embeddable common Lisp, this was another thing that was suggested because like, oh, the garbage collector isn't so crazy, or I mean, not crazy, but it doesn't need as much support. But it still uses some of these tricks that we had to avoid. So we had to modify that anyway. And I mean, ECL still does some kind of runtime. There's still some kind of runtime compilation. I don't necessarily know that the way ECL is set up would have allowed us to escape some of the restrictions that were on the system. So it was unclear whether a system like ECL would allow us to bypass. I mean, surely there would be less issues, but some of the issues would have still been there. And of course, there was the performance was a big issue that we were already envisioning having problems with. And I mean, as seen in the demo, there's it's better now, but there's still hitching even with SBCL, which is orders of magnitude faster.
Did I understand correctly that you have to compile some effective methods at runtime, and so you do an interpretation of them? Why can't you just figure out which 3 or 4 effective methods have to be done at runtime and just pre-compile them?
So you don't see Christoph laughing behind you, but yes, so that is an idea, right? And I have a hack in place now that tries to pre-bake as much of class as possible. It's very ugly. I don't know what it's doing because I don't understand PCL, and I don't know anybody does. But it's in some cases it's very tricky to do that because the set of possible arguments can be extremely large. And I think right now what PCL does is like it aborts at a certain point. Like if it says there's too many possibilities, I'm just going to cut it off. And I don't know yet how to curse it to just do the cache for everything. But that's like with the pre-baking, we only get a couple of compile calls. So we did instrument this. And it doesn't seem to have enough of an impact anymore to be like super urgent. It would still be nice for like deployments everywhere on PC as well to just be able to bake everything as much as possible.
So I assume you profiled the slow loading, and is it just literally bringing stuff into RAM and doing that relocation you talked about, or is there something else interesting going on during that time?
So yeah, we did have some logging. Actually, it does take a non-trivial amount of time to just map everything into memory because the operating system doesn't have like actual mmap. You do have to like copy stuff in, and then yeah, even you have to zero out some of the spaces manually, and that takes some time. And just generally like the startup there. So I think actually a significant amount of time is not even into the game engine. It's just like what SBCL has to do to start up on its own. And I think it's just because maybe we haven't necessarily figured out all the virtual memory. So the operating system doesn't expose much for us. But we had to, when they didn't have some virtual memory thing that another Unix-like operating system would expose, you had to do the more brain dead, like copy stuff, move stuff around. We don't know, maybe there's a better way to do it.
My current idea is to just like set it up so that it displays a splash screen as early as possible. Yeah, cool. The age-old trick.
Yeah. Secondly, really quick, at some point it was like in the presentation, oh, just make everything relocatable. That sounds like it would have been super hard. Was that like a huge deal, or?
So actually there was work done before to make the majority of the spaces, like the heap, relocatable, because this is something that other people have wanted for different contexts. The hard thing was that there was a space that was very assumed to be hardwired. So this space had like nil in it. Things like these where it's like really like the compiler liked to assume that nil was always going to be in the same place always, and hashes were based on nil. So this is a feature called relocatable static space that I implemented on ARM. Actually recently, someone else, another SBCL developer, has decided they wanted to and then ported it for x86. So yeah, it was difficult. It was non-trivial to actually do. It is a major effort sometimes to get these pieces working. So no, relocatability was definitely one of the main issues to solve. And this code constant relocation, that was also another big thing that these were the issues that made me even think like this isn't possible after all.
One question from my side, 2 questions actually. If you are already running the SBCL interpreter, what is preventing you from having a REPL on the switch itself?
What's preventing us from doing that is that their licensing agreement forbids us from exposing that kind of functionality.
Not really exposing, I mean for your development purposes.
Yes, so what's preventing us from doing that is nothing. We have done that. That was one of the earliest demos we did. The problem is that input is extremely annoying and cumbersome on the device, so using that for debugging is kind of a dead end anyway. Okay,
thank you. The second question, do you know if the second version of the switch is going to impose any new programming constraints on you, in addition to no new pages, write X or execute and so on?
We don't assume so. So we don't know for sure, obviously, because nobody has the device yet except for like select developers and Nintendo themselves, of course. but it's still an ARM system. It's still got an NVIDIA GPU integrated into it. It still uses a descendant of this operating system. So I don't really see anything else they could have done worse. Like, if anything, they're going to be more permissible with what they do at some point, because some games do require JIT to go fast. So.
Any more questions from the room? What? Hang on.
How do you get it on the switch? Do you need to have like a hex switch, or can you put it on there in some other way?
So you need to buy a development kit, which is this thing. So this is like a special unit. It doesn't look different, but it is slightly different. And then you get this dongle that lets you connect it to the PC. And then you also get access to their SDK, which is all Windows stuff. So lots of fun with virtual machines.
Have you tried running Zhang and connecting with Slime?
So networking is one of the things that is mysteriously not working. I don't know why, because they have BSD sockets, as most things do. But for some reason, whenever I try to call out to the internet, it just doesn't work, and I don't know why. It's very bizarre. Their documentation is, well, sometimes good, sometimes, well, anyway.
But theoretically, it should work.
Okay, I have one more question. For where you mentioned that instead of being able to JIT, you have to run the interpreter, that sounds like it's a tree walking interpreter, not a bytecode interpreter?
That's right, yeah. So SBCL only has 2 tree walking interpreters. So there's an old one which is very, very simple, and it does like the very basic interpretation. And there's a newer one which is a bit smarter about the tree walking interpreter. And there used to be a bytecode interpreter in SBCL as well, but that was really ancient and was removed. So no, there's no bytecode going on. That would probably make things go faster.
Yeah, I mean, that was sort of going to be my next question. I don't know if you have profile information or whatever, but do you envisage the fact that that is interpreted being a problem in removing that flickering from Candria, or
so it's a bit hard
fixing
to
performance in general?
exactly figure out how much of an impact that's having, because in a profile, if it's something like method dispatch, that's not going to be very easy to discern from the profile how much of that is because this bit is being interpreted. So when we went from less than 1 frame per second to like, I think what now, 40, 50 consistently, 30, 40, it was from solving higher level optimizations with the game engine itself. So I expect we're probably going to have a lot more wins from actually making the game engine faster rather than this kind of low-level detail. So I don't think we're quite at the level where this is becoming a bottleneck yet.
Okay, cool. Then I think we're done. I would just like to repeat what Yukari said at the end. This has been, I know, a very big personal investment for her. She's put a lot of her own limited personal resources into this project. To quote a great man, give her your fucking money.